The universe is 13.8 billion years old. Stars have been burning for most of that time. They will continue for another 100 trillion years. And then, for a span so long it takes 4 digits just to write the number of zeros, the universe sits in absolute darkness until something explodes. Was it the last event in all of existence, or just the last one anything could witness? Right now, roughly 2 trillion galaxies fill the observable universe. Stars burn hydrogen into helium, planets orbit, and light travels between them at 300,000 kilometers per second. This is the Stelliferous era, the age of stars. And according to astrophysicists Fred Adams and Gregory Laughlin, who mapped the future of the cosmos in a 1997 paper published in Reviews of Modern Physics, this era is the second of 5. We are living in the early morning of a day that stretches for timescales so extreme they require their own notation. After the stars go out, 4 more eras follow. Each one is longer than everything before it combined. Each one is emptier. And the last event on the timeline sits at a number so large it takes 3 layers of exponents just to write it down. This is the full story, from now to the final measurable moment. Before the universe changes in any way a human could detect, Earth changes first. 1 billion years from now, the sun is 10% brighter than it is today. That is enough to end life on Earth. Water vapor rises into the upper atmosphere, ultraviolet light splits it into hydrogen and oxygen, and the hydrogen escapes into space. Earth does not explode. It dries out the same way Venus did, through physics, not catastrophe. The Voyager. One spacecraft, launched in 1977 and now roughly 25 billion kilometers from Earth, drifts without power through interstellar space, its plutonium-238 fuel long since depleted, its golden record carrying greetings in 55 languages to a silence that will never answer. Long before the universe notices, everything human is already gone. 5 billion years from now, the sun exhausts its hydrogen fuel. It swells into a red giant large enough to swallow Mercury and Venus. Whether Earth survives is still debated. Schroeder and Smith calculated in 2008 that Earth sits right at the boundary. Tidal drag from the expanding sun could pull our planet inward. The outcome depends on how much mass the sun sheds during expansion, and current models do not agree. But here is what does not depend on any model. The sun is ordinary. It is one star among 200 billion in this galaxy alone, and it is not the last. The smallest red dwarfs, stars with barely 8% of the sun's mass, burn their hydrogen so slowly that they will shine for approximately 10 trillion years. That is more than 700 times the current age of the universe. A star called TRAPPIST-1, just 41 light-years from Earth, weighs 9% of a solar mass. According to models by Laughlin, Bodenheimer, and Adams published in the Astrophysical Journal in 1997, stars in that mass range convect their entire hydrogen supply through the core. Nothing gets stranded in outer layers. They burn everything. To put that lifespan in perspective, if the entire current age of the universe were compressed into a single day, a red dwarf would burn for 2 full years. The stars we barely notice today will outlast everything we have ever observed by a factor most calculators cannot display. When the last red dwarf exhausts its fuel, roughly 100 trillion years from now, the Stelliferous era ends. Star formation stopped long before that. The gas between galaxies was depleted. Molecular clouds collapsed into their final generation of stars, and then there were no more clouds to collapse. The Milky Way and Andromeda may or may not have merged by then. A 2025 study by Sawala and colleagues, published in Nature Astronomy, used updated Gaia measurements of Andromeda's sideways motion and found only a 2% probability of a head-on collision within 5 billion years. The overall chance of any merger within 10 billion years is roughly a coin flip. But it does not matter. Merged or separate, the galaxies go dark on the same schedule. The cosmic microwave background, that faint afterglow of the Big Bang still detectable today at 2.7 Kelvin, redshifts below the detection threshold of any foreseeable instrument. Beyond a certain distance, the expansion of space outruns light itself. Galaxies that were once visible disappear behind an event horizon that has nothing to do with black holes and everything to do with the accelerating growth of space between them. The sky is not just dark, it is permanently, irrecoverably empty. The universe after stars is not empty. It is full of corpses, white dwarfs, neutron stars, brown dwarfs that never had enough mass to ignite hydrogen fusion, and black holes at the centers of dead galaxies. This is the Degenerate era, and it lasts from 10 to the power of 14 years to roughly 10 to the power of 40 years. That range depends on a single, unanswered question. Do protons decay? Every atom is built from protons and neutrons. The standard model of particle physics says protons are stable, they do not break down. Grand unified theories that attempt to merge 3 of the 4 fundamental forces predict that protons have a finite lifetime. They will eventually fall apart into positrons, pions, and radiation. No one has ever observed proton decay. The Super Kamiokande detector in Japan is a tank containing 50,000 tons of ultra-pure water buried 1 kilometer underground, and it has been watching since 1996. It set a lower bound of 2.4 times 10 to the power of 34 years. That result ruled out the earliest predictions. But newer models predict proton lifetimes from 10 to the power of 34 to 10 to the power of 36 years, right at the edge of what current instruments can detect. Hyper Kamiokande, the successor detector with 8.4 times the volume, is expected to begin collecting data in 2027 or 2028. If proton decay exists in that range, this experiment will find it. If protons do decay, the consequences are total. Every white dwarf, neutron star, brown dwarf, planet, asteroid, and grain of dust disintegrates. Atoms do not just stop working, they erase themselves from existence. The Degenerate era ends not with a bang, but with a slow dissolution of matter into radiation and subatomic debris. If protons are stable, something stranger happens. The corpses persist, and trillions of years later, some of them explode. If that idea just made you reconsider how this story ends, subscribe. This series goes further than anything you have seen on this topic. Assuming protons are stable, white dwarfs cool over trillions of years into objects called black dwarfs. No black dwarf exists yet anywhere in the observable universe. It takes roughly a quadrillion years for even the oldest white dwarfs to radiate away their residual heat and reach a temperature effectively indistinguishable from absolute zero. A black dwarf is a crystalline sphere, its atoms locked in place by degeneracy pressure. And somewhere in the far future, one of these dead stars will explode because a single atomic nucleus tunneled through a wall it should never have been able to cross. The process is called PYCNO nuclear fusion. At zero temperature, quantum mechanics still permits adjacent nuclei in the crystal lattice to occasionally tunnel through their mutual electrical repulsion and fuse. The probability per pair per year is absurdly small. But the timescale available is not small. In 2020, physicist Matt Caplan published a paper in Monthly Notices of the Royal Astronomical Society showing what happens over 10 to the power of 1,100 years. The Pykno nuclear reactions slowly convert silicon-28 in the black dwarf core into nickel-56, which decays into iron-56. Iron has fewer electrons per nucleon than silicon. As iron accumulates, the effective Chandrasekhar mass limit drops. When that limit drops below the actual mass of the black dwarf, the result is catastrophic gravitational collapse, a supernova. The same kind of thermonuclear explosion that created most of the iron in your blood, except triggered not by accretion from a companion star, but by quantum tunneling over 10 to the power of 1,100 years. Caplan calculated that black dwarfs between 1.16 and 1.35 solar masses qualify. Our Sun, at 1 solar mass, falls just below the threshold. It will become a white dwarf first, then cool into a black dwarf over trillions of years. But it will never accumulate enough iron to collapse. It will sit in the dark forever, a frozen crystal sphere roughly the size of Earth with the mass of a star, doing nothing for eternity. Not even decaying, if protons are stable. Just existing, cooling imperceptibly, for timescales that make the current age of the universe look like the first tick of a clock that has not yet started counting. The black dwarfs that do qualify amount to roughly 1% of all the stars that ever formed. About 1 billion trillion objects. The first of these explosions occurs at 10 to the power of 1,100 years after the Big Bang. The last ones, from the least massive qualifying black dwarfs, detonate at 10 to the power of 32,000 years. Not one of these explosions has happened yet, not once, anywhere, in 13.8 billion years. And by the time they occur, the expansion of the universe has carried every black dwarf so far from every other that no explosion will ever be witnessed by another object. Each one detonates alone, in absolute darkness, observed by nothing. One additional condition. Caplan's entire scenario depends on protons being stable. If protons decay, the black dwarfs dissolve into radiation long before pycnonuclear fusion can accumulate enough iron to trigger collapse. The last explosions in the universe depend on an experiment that has not yet delivered a result. After the last black dwarf supernova, or after the last proton decays, whichever comes first, the universe enters its fourth era. Only black holes remain as organized structures. Everything else is radiation, subatomic particles, and the expanding void between them. Black holes are not permanent. In 1974, Stephen Hawking showed that quantum effects near the event horizon cause black holes to emit a faint thermal radiation. The process is extraordinarily slow. The temperature of the radiation is inversely proportional to the black hole's mass. A stellar mass black hole, roughly 3 solar masses, has a Hawking temperature of about 20 nanokelvins. That is colder than the cosmic microwave background is today, which means stellar mass black holes are currently gaining mass, absorbing more energy from the universe than they emit. They will not begin to shrink until the cosmic microwave background cools below their Hawking temperature, hundreds of billions of years from now. Once net evaporation begins, the timescale depends on mass cubed. Double the mass, multiply the lifetime by 8. A stellar mass black hole evaporates in approximately 10 to the power of 68 years. A supermassive black hole with tens of billions of solar masses, comparable to the largest known objects like Phoenix A, evaporates in approximately 10 to the power of 100 years. A 1 followed by 100 zeros. A Google. Write down every atom in the observable universe, and you reach 10 to the power of 80. The lifetime of a supermassive black hole is a number that dwarfs the number of atoms in existence. It is not just a long time, it is a quantity that makes the physical universe look small. In its final moments, a black hole's evaporation accelerates. The smaller it gets, the hotter it becomes. The last fraction of a second produces a burst of gamma rays and particle-antiparticle pairs. Then it is gone. No remnant, no debris. Just radiation expanding into a universe that is by then almost entirely radiation. When the last supermassive black hole evaporates, roughly 10 to the power of 100 years from now, the black hole era ends. The universe enters its fifth and final state. The dark era is not an event, it is a condition. The universe contains photons, neutrinos, electrons, and positrons, all drifting apart at velocities so low they approach zero. The temperature of the universe asymptotically approaches absolute zero, but never reaches it. Entropy is at its maximum. Nothing can happen because there is no free energy to drive any process. This is the heat death of the universe, and under the standard model of cosmology, it is permanent. But 3 speculative possibilities remain on the table, each more improbable than the last. First, at a timescale of roughly 10 to the power of 10 to the power of 50 years, quantum fluctuations in the vacuum could spontaneously assemble a functioning brain, complete with false memories of a universe that no longer exists. This is the Boltzmann brain problem, named after 19th century physicist Ludwig Boltzmann, and it was formalized by Dyson, Caplan, and Susskind in a 2002 paper published in the Journal of High Energy Physics. It is not science fiction. It is a mathematical consequence of quantum mechanics applied to infinite time. The probability is vanishingly small in any given volume of space in any given year. But the dark era is not any given year. It is all the years that will ever exist, and in that context, the math does not care how unlikely an event is. Most cosmologists treat this as a constraint on viable theories rather than a literal prediction, but the equations do not exclude it. Second, at a timescale requiring nested exponents to even write down, quantum mechanics permits a Poincare recurrence. Every possible arrangement of particles in the observable universe has a finite probability of recurring by chance. Given enough time, a state macroscopically identical to the present will reassemble spontaneously. The timescale derives from the de Sitter entropy of the cosmological horizon, approximately 10 to the power of 122. The recurrence time is the exponential of that entropy. To give you a sense of what that means, the number of digits in the number of digits in this timescale is itself a number with 122 digits. There is no analogy that makes this comprehensible. It is simply the largest meaningful number in physics. Third, vacuum tunneling. The quantum vacuum of our universe may not be the lowest possible energy state. If it is metastable, a random quantum fluctuation could nucleate a bubble of lower energy vacuum that expands at the speed of light. Inside that bubble, the fundamental constants of physics are different. Whether this constitutes a new Big Bang depends on the resulting vacuum structure. The Coleman-de Lucia instanton, described in 1980, provides the mathematical framework. But unlike Poincare recurrence, this is not a return to the same universe. It is something else entirely. In March 2025, the DESI collaboration, the Dark Energy Spectroscopic Instrument, published its second data release, the largest galaxy survey ever completed, mapping over 14 million galaxies and quasars using baryon acoustic oscillations. The results showed a 3.1 to 4.2 sigma preference, depending on which supernova datasets are included, for dark energy that weakens over time rather than remaining constant. If confirmed by Euclid, SphereX, and the Vera Rubin Observatory, the far future may look fundamentally different from what we just described. The assumption that powered every prediction in this video, that dark energy is a cosmological constant, is now under direct experimental scrutiny for the first time. The universe is 13.8 billion years old. The last black dwarf supernova, if protons are stable, will not fire for 10 to the power of 1,100 years. To write that number out in full, you would need more digits than there are particles in the observable universe. We are not at the beginning of the story. We are so early that the word beginning does not apply. We are in the first fraction of the first heartbeat of a process that has not yet taken its second breath. And the one experiment that determines which future actually arrives has not finished collecting data. The next video covers what lies between galaxies and the distances involved. If 10 to the power of 1,100 years unsettled you, the space between those detonating black dwarfs is worse. Tell me in the comments which era of the future unsettles you most.